Okay, so in this video we're going to talk about electrolysis. And remember when we talked about electrochemical cells, we said there's two types of electrochemical cells, one of which involves spontaneous reactions and one involves non-spontaneous reactions. The spontaneous reactions are called voltaic cells, or otherwise known as galvanic cells, and those can be used to make batteries because they will generate a flow of electricity. And electrolysis is the opposite. These are non-spontaneous, and you'd have to actually hook up a direct source of current to make these cells go. This can be used in electroplating, which we'll see some examples of. But going back to general overview, electrolysis is non-spontaneous, meaning the delta G value will be positive, and since delta G equals negative NFE, that means our E value here should be negative. So we should find with these ones that we end up with a negative cell potential when we calculate that cell potential. So there's a couple of topics, kind of two main themes that two main types of questions that you might see with electrolysis. And one has to do with just what's happening in the cell, who's being oxidized, who's being reduced, what's the cell potential. And then the second part will involve some quantitative questions. So if you were, for example, electroplating something, you might say, if I hooked up this much current for this amount of time, how many grams of copper might I be able to plate onto this sample? So that is doing some calculations. So this video will just deal with what's going on in the cell and how to determine who's being oxidized, who's being reduced. Here's an example of an electrolytic cell. Let's say you are going to hook up a current to an aqueous solution of calcium iodide. So similar to our voltaic cell, we've got an anode, we've got a cathode. In this case, those are likely to be made of an inert material such as platinum. And the same thing happens in an electrolytic cell as in a voltaic cell. So remember in terms of the anode cathode. So remember an-ox. So at the anode, oxidation is occurring. And red cat, so at the cathode, reduction is occurring. And remember, oxidation means that's where you're losing electrons. So the anode side of it, where the oxidation occurs, that is where the electrons are going to start from, and electrons are going to flow in this direction towards your cathodes. That will be the flow of electrons. Notice that in this solution, both electrodes are immersed in the same solution, so they're not separated out, unlike in a voltaic cell. So the question is, if we want to figure out what the cell potential, so what is the cell potential here? And the cell potential is our E value, and we'll assume standard conditions. You have to ask yourself, who is going to be oxidized and who is going to be reduced? So let's look at who is going to be reduced first. That might be the simpler one. Who will be reduced? And just like we said with voltaic cells, the substance that has the most positive reduction potential is going to be reduced. So you have to ask yourself, what is present in the solution? So I've got aqueous calcium iodide. That means I have calcium ions, I've got iodide ions, I've got waters. And reduction is gaining electrons. So if we think about our options here, I've got calcium ions could gain electrons to form calcium. And if you look at your table here and find calcium, what you want to do is you just want to scan through your table. That's near the bottom. It's got an E value of negative 2.87. Okay, and I will look for example where water is reduced. This one you're not likely to be able to just guess what the products are of that reaction. But what you want to do is you want to scan through your table of reduction potentials, and you're looking for a reaction where water and some electrons are on the same side of the arrow. Okay, where they're over here on the left side of the arrow. So if you scan through that, and this is important because there are multiple reactions here that involve water. So you want to make sure you're looking at the one where the water and electrons are on the same side of the arrow. So if I scan my way down, and that reaction is down here, where it shows the reaction is actually 2 waters and 2 electrons. will form hydrogen gas and 2 hydroxides. And the E value there is negative 0.83. And I also have iodine in solution, iodine ions. A reduction would be gaining electrons. And iodine is already negative. It's not likely to gain more electrons. So if you notice on your table of reduction potentials, there is no option that shows negative iodine gaining electrons. There's an example showing neutral iodine gaining electrons, but not the negative iodine ion. So this reaction is not going to occur. We'll take that out as a possibility. So in general, when you are doing electrolysis of an ionic solution, your options for things that might be reduced would be either your cation or H2O. Your anion's not likely to gain any more electrons. It's already negative. And then what you want to do is you want to look at these two reactions. And in this case, they're both negative, so a little different from what we might be used to. The value that is the most positive will be the most likely to occur. So even though they're both negative, this one right here is less negative. So what that means is water is going to be my substance that will be reduced over here at the cathode. So the cathode, water is going to be reduced. Okay. As far as who is going to be oxidized. Again, let's look at our species in solution. First of all, I have, to begin with, I've got my calcium ion. Remember, oxidation is, if you think Olay, is losing electrons, becoming positive. Since calcium is already positive, it is not likely to become any more positive. So my calcium ion is not going to be oxidized. Let's look at our other options. Who else could be oxidized? Well, let's see, could water be oxidized? We want to look for a reaction where, in order to be oxidized, I lose electrons, right? So that means we're looking for a reaction where water is on one side of the arrow, the electrons are on the other side of the arrow. Notice how in this case, water and electrons are on the same side of the arrow. For the oxidation, we're looking for one where the water and electrons are on opposite sides of the arrow. So if I scan through, I will see that near the top here, I have a reaction where water and electrons are on opposite sides of the arrow. The problem is the way it's written, it looks like a reduction, because these are all written as reductions, right? So I will write down the reaction as written. It's O2 plus 4H plus and 4 electrons makes 2 H2Os. Okay, this is written as a reduction. And again, the way I spotted that is I noticed the electrons and waters are on opposite sides. So if I take this and I flip it around, I'm going to take this whole thing, make my products to reactants and vice versa. Now this reaction is 2H2O, releases 4 electrons and 4 H pluses and 1 O2. I just took my reduction that was given to me and turned it into an oxidation. And remember, when I flip around these reactions, the sign of E will change. So if the value of E here, given on my table of reductions, is plus 1.23 volts, the E value for the opposite reaction, E will be negative 1.23 volts. So this is one possible oxidation. So again, to find possible oxidations, I have to take my reductions that are given, flip them around, and remember that flips the sign. Alright, so I already ruled out calcium ions. We've got the water written down. The other thing that we need is to look at is iodine. So, iodine ion. So I want to have a reaction that shows my negative iodine ions losing electrons. And I'm going to scan through my list and see up here in like the top third, I see a reaction involving iodine. The way that it is written on our table, I'll use a different color pen. it's written as a reduction, so it looks like this. Solid iodine and 2 electrons will make 2 iodine ions, and that has an E value of plus 0.53 volts. Okay, in my solution, first of all, I want it to look like an oxidation instead of a reduction, so I'm going to flip it around. And in my solution, what I have present is iodine ions. I don't have I2, so I want to make sure that my I minus ions are over here on the reactant side. So if I take this reaction, flip it around, it is 2 iodine ions will make 2 electrons and 1 I2 solid. And when I do that, when I flip a reaction around, my sign of E changes. So if my reduction is plus 0.53, my oxidation is negative 0.53 volts. So now I have my 2 possibilities for my substances that can be oxidized. And again, if you think about your relationship delta G equals negative NFE, the process that has the more positive E value will have a more negative G value, so it's more likely to occur. It's more energetically favorable. So once I've taken a look at my possible reactions and I've flipped them around and turned them into oxidations, and I've flipped the signs accordingly, then the process as written that has the most positive E value will be the most likely to occur. So in this case, again, both E values are negative, just like they were up here, but the one that is least negative is the most positive value, and this will be more energetically favorable. So it's this reaction right here. So what that means is, over here at the anode, your iodine ions are going to be being oxidized. So I draw what's happening. These will be turning into I2. And then over here at the cathode, the reduction, your water is going to be being reduced. As it does that, it looks like it forms H2 gas and hydroxide ions. So if you look at the solution over time, you would see bubbles. If you put an indicator in it, you'd notice it would start to turn basic as your water is reduced. So this is my electron generating reaction. This is my electron taking reaction that's occurring in this electrolytic cell. And then if you wanted to find the overall cell potential, I would just add up these 2 values. Again, notice I've already flipped this reaction around. I've already flipped the sign around, so I'm just going to add them up as written. And that will give me the voltage for the overall process. And I can also write out the overall reaction that occurs, kind of like we do in Hess's law. So I've got 2 waters and 2 iodines and 2 electrons. Make 2 electrons, 1 hydrogen gas, 2 hydroxides, and 1 solid iodine. Notice how your number of electrons cancel out. They should, because your number of electrons gained needs to equal how many you lost. And your E values, you just add them up. So negative 0.8, negative 0.5, you've got a value of negative 1.36. I hope my math is right there. Notice how, again, my cell potential is negative, meaning I have a positive delta G value, meaning this whole thing is non-spontaneous, which is what I would expect, because we said at the beginning this was electrolysis. Electrolytic cells are non-spontaneous. They require a source of current in order to make this reaction go.